Hi there. Today we're looking at extracting training data from large language models by what appears to be a big collaboration between corporations and academic institutions. There are almost as many affiliations here as there are authors. So this is joint work between, as you can see, many sort of institutions. And it is a pretty cool paper. So the high-level topic is that these authors take large language models, as the title says right here, and trained large language models specifically, and they're able to extract training data just from the trained model. In fact, just from the black box access to the trained model. And not only are they able to extract training data, they are able to extract pieces of training data, sort of verbatim, that have appeared only very few times in the training data. That's what they call a form of memorization. So they're able to extract these with a kind of pretty clever attack. So if you look at this prime example right here, they are able to query GPT-2 in this case, which is one of these large language models, to output this piece of text. And the black stuff here is by the authors to protect the sort of privacy of this individual right here. This is a real piece of text that they actually got out, and you can verify that. So they're able to extract this just from GPT-2, and needless to say, this has consequences for security and privacy and so on, because if you train one of these models with, let's say, internal or private data, user data, and so on, you have to be worried that these models are going to just output that data again on the other end and potentially leak information. This, of course, has not been a problem that much so far once we just trained image classifiers and so on. But here, especially with only black box access, this seems like it has some consequences. So we'll go over the paper, we'll go over the attack or the technique the authors devise, which is, I think, pretty clever. We'll go over sort of the results that they get from using this on a GPT-2, and we'll go over my opinion of the paper, which I can already tell you. My ultimate opinion is that the attack is cool, the concerns are valid, but the paper is probably written a little bit more scary than it ultimately seems. In fact, I find the results, the actual results of this paper fairly okay, like fairly promising, and sort of straightforward, not that scary. And also, the paper is interesting from another perspective, namely from the perspective of what it tells us about these language models and how they work. And it sort of strengthens a number of hypotheses that I've put forward in my video about GPT-3, about how these models work. And that's also fairly cool to see in this paper. So we're going to jump in here. And as always, if you like content like this, don't hesitate to share it out, or subscribe, I should say, if you're not yet. All right. So they say it has become common to publish large, so billion parameter language models that have been trained on private datasets. This paper demonstrates that in such settings, an adversary can perform a training data extraction attack to recover individual training examples by querying the language model. Right? So we already have quite a bit of information right here. So large language models have been, of course, trending with, especially since GPT-3, but at least since the advent of the transformers, BERT, and so on. Though BERT isn't exactly a language model. So language models are models that, given a piece of text, predict the next word. It's so easy as that. Or they predict a probability distribution over the next word. So if you say a cat sat on, so that's the input. The language model would give you a probability distribution over the next word. So the next word might be the, or the next word might be a, or the next word might be next, because of next to and so on. And it will sort of give you a probability distribution over each of these words. That kind of looks like a face. It will tell you how likely each next word is and so on. And then you can sample from it. You can sort of choose one of those words and then go on. And you can evaluate the likelihood of entire sequences and so on. So GPT-3 is one of those large language models. And these large language models, they've been, of course, since they are large, we know that they also need a lot of data to be trained on. So a large language model would take like a giant piece, a database of training data, which is scraped from the internet usually. So this is too much to simply be curated by humans. They just let scrapers run over the internet. Then they use this to train the model, whatever that is, in GPT-2 in this case. And GPT-2 will then be a trained model. So you sort of throw the training data away and you simply say, this is our model now. We're going to publish this, right? Now, the problem is if there is a piece of data in here that is kind of secret and you think, well, it's just one piece of data. Like how much can go wrong, right? The problem is if I can inspect GPT-2 and recover this exact piece of training data so that GPT-2 will output that exact piece, right? That is a problem. Now, they make some good points here. This notion of a piece of training data and what it means to memorize a piece of training data and what it means to extract one is fairly fuzzy, and they go quite a bit deeper in this paper. So they have kind of strict definitions. They say, we demonstrate our attack on GPT-2, a language model trained on scrapes of the public internet, and are able to extract hundreds of verbatim text sequences from the model's training data. These extracted examples include public personally identifiable informations, so names, phone numbers, and email addresses, as you saw on the right here, IRC conversations, code, 128-bit UUIDs, and so on. So they are able to extract all of these things from the trained model, right? And this, you can already see that how this can become a problem. They say our attack is possible even though each of the above sequences are included in just one document in the training data. And this notion of memorization here and when it is dangerous, they correctly say that this is only dangerous, of course, if the training example is contained in, let's say, only one piece of training data. Because if something is contained in thousands of pieces of training data, it's okay to memorize that, right? If a name of like some famous person is memorized, and maybe that the address, like the president of the USA lives at the White House, that it is not a secret, right? So it is okay if your language model remembers that, because it probably occurs in many training data points. However, if something is contained in just one document, right, and the model remembers it, then that is, kind of true memorization. It is not maybe, or, it's probably not learning anything from that data point. It's simply memorizing it to make its training loss lower. So that's the case on the right here. Though I have to say, this, as I said, it's written a bit more scary. So they don't exactly say that this name and phone number is contained in just one document. And they also say, like, this is on the public internet. GPT-2's training data was scraped from the public internet. So here is sort of my first investigation into this. Of course, you can Google this and you'll find it. You'll find this. And even though, the blacking out here also is a little bit of, I think it's a little bit gimmicky, because I don't see a problem with disclosing this particular piece of information, and I'll show you why. So when you search for it, you'll find the NIST homepage. You'll find a cryptographic algorithm validation program, and you'll find that this is a description of a software implementation, and here is the personally identifiable information. You can see this is a corporate address. So this is the address of a corporation, and the contact information is a corporate contact. It's a corporate email address, it's a corporate phone number, and so on. This is the exact thing right here. And with respect to it only being present once in the training data, so if you actually if you complete the name here and search for this, you'll find many results. Now, I don't know how many of these results are actually from, in the GPT-2 training data. No one knows that except OpenAI. But there's 2 Google pages of results, but Google has deduplicated some of them. And now if I click on all, there are 9,000 results for this. And they are not all the same. Oh, no. So if you look at a bunch of those, you'll see that they are almost the same. But here at the bottom, as you can see, this changes. So, depending on your scraper, these all count as separate websites. And therefore, I'm not so sure that this particular piece of information here is contained only once. Plus, it is a corporate contact. So again, to my point, the paper might be written a bit more scary than it ultimately turns out to be. Though, you have to make 2 different points. Like this particular piece of information, yes, it might be written a bit more scary and gimmicky with the blacked out stuff. However, right, the paper has a point, namely that if, let's say, you as a company do this on internal data, it might very well be, and they do have examples where they reproduce data from just one document. But even it might be that something like this happens to you internally, where you maybe in your internal document base, you quasi-duplicate a document with the same information over and over, and that's not deduplicated, and then your language model memorizes that. So it's it has a point, the paper. That's what I'm trying to say. I hope that's clear. All right, so we'll get to the results in a bit. I hope I've already given you some sort of a taste for what you can expect. So first of all, they go into language models, into the definition of language models. And the language model here is simply framed as a model that can give you a probability of a sequence of text in a stepwise fashion. So always probability of next word given the previous words, and you can evaluate that, right? So the access to the model that they assume here is access to, let's say, the logits of the model or the output distribution of the model. They say they use GPT-2 because it's trained on large piece of text, but it's also you can evaluate it. It's not as slow, I guess, as GPT-3, and it's publicly available. However, the training data to GPT-2 is not publicly available, but they do have someone of OpenAI on the paper here, and this person at OpenAI they could query the OpenAI person to make sure a given piece of text that they find is or isn't in the training data of GPT-2. So that's how they work. So that the OpenAI person acts as an API for the training data, right? So they do they define their attacks here. So they do a lot of things to set up cleanly what they do right here. So they have 2 points right here. There is this notion of memorization. Okay, so they say there are many ways to define memorization in language modeling. In this particular piece of work, they say it is okay to memorize some stuff. They say language models must, for example, memorize the correct spelling of individual words, right? Because the words are made of word pieces and the language model needs to output that. So that's fine if it memorizes this. Indeed, there is an entire area of research that analyzes neural networks as repositories of memorized knowledge. For example, when GPT-2 is prompted to complete the sentence, my address is 1 Main Street, San Francisco, CA, it generates the next token, 94107, a correct zip code for San Francisco in California. They say, while this is clearly memorization in some abstract form, we aim to formalize our definition of memorization in order to restrict it to cases that we might consider unintended. Okay, so memorization as such isn't bad. What is bad is what they call here the eidetic memorization of text. So eidetic memorization of text is when the model memorizes something that only appears very few times in the training data. So they say, we first define what it means for a model to have knowledge of a string. Our definition is loosely inspired, yada, yada, yada. A model F knows a string if S can be extracted by interacting with the model. So if you can input whatever you need to input and the model outputs S, then you say that model knows S, right? So if S is a piece of training data, then you say the model memorizes S. The model has memorized it. So here they say a string is extractable from a language model if there is a prefix, and the prefix here is the input to the model, such that if you input that model, the output will be the string. And then they define this eidetic memorization. Respectively, they define k-eidetic memorization. A string S is k-eidetic. I have no clue whether I pronounce this correctly. K-eidetic memorized by a language model, F, if S is extractable from F, so that's memorization, and S appears in at most k examples in the training data. Okay, so if this address of this person only appeared twice, but you could extract it verbatim from the language model, then that would be an example of 2 eidetic memorization, okay? Because k in that case would be 2 because it appears twice in the training data. Though they are not clear what they mean by examples in the training data, because usually this training data is sort of chunked to make it fit into the language model and so on. And I think they do this on a document basis. So they would consider something like this here, one example, right? And then a different document, a different example. So if you have like, for example, if you have these IRC conversations that they are able to extract. So they claim here they are able to extract IRC conversations, or they're able to extract the usernames of the IRC conversations, right? The usernames might appear hundreds or thousands of times because they chat with each other, and it will all be, in one document. But the document will be so long that will actually be chunked into different training data pieces. Maybe, I don't know. I don't know exactly what it means to be an example right here. But they do the example for sure. A piece of text can appear more than once, even if it is only in one example. In fact, they actually analyze this situation. All right, so we've defined that this is these k-eidetic memorization. That's what we're looking for. That's sort of the problematic regime. If k is very small, in the extreme k is 1. One piece of training data contains a string, and we can extract the string from the trained language model. They also say that for any given k, memorizing longer strings is also intuitively more harmful than shorter ones. So this kind of makes sense. And they even go into sort of corner cases. They say it admits certain pathological corner cases. For example, many language models, when prompting with the sequence, repeat the following sentence, and then you give a sentence, will do so correctly. This technically allows any string to be known under our definition. But they of course don't do that. They assume they don't know the training data, so they can't just say repeat the following sentence and so on. But you do see that it is fairly hard actually to even define the problem right here, even though we as humans have a sort of an intuition what it means for a language model to unintentionally or due to unintended memorization. All right, so the adversary's objective here is to extract memorized training data from the model. The strength of the attack is measured by how private, so how k-eidetic a particular example is. Stronger attacks extract more examples in total and examples with lower values of k. They say we do not aim to extract targeted pieces of training data, but rather indiscriminately extract training data. While targeted attacks have the potential to be more adversarially harmful, our goal is to study the ability of language models to memorize data generally, not to create an attack that can be operationalized by real adversaries to target specific users. So you can see that here they simply want some training data. They don't really care what it is. They simply want to get some. So they're going to search for sort of the easiest to get training data. And so they frame it as, yeah, we don't want to devise an attack that can attack individual users, but there is a different component to it. So if you had to sort of guess the password of any particular user, that would be, fairly hard. However, if you had to guess a password that was used by any user, it's fairly easy, right? Even if you discard the fact that most of people use password as password and so on, if people would just uniformly sample words from the dictionary as their password, still you'd have a decent chance of figuring out a password, right? You have a decent chance of figuring out, not super high entropy things like maybe credit cards. You'd have a decent chance of figuring out the credit card number just by guessing one. So this is the regime we are in here, and it's entirely different regime, I think, if you try to attack individual users. Essentially, what they're going to do right here is they're going to say, look, there's training data right here. Now, some training data, these models can extract a pattern from, right? And this is what we do with machine learning, right? We say, okay, this data right here, they all have like some pattern, and this data right here is some pattern, and you can learn from this, and it has some pattern. So the machine learns to sort of abstract from its training data samples and so on. But here is a data point that doesn't really fall into any of these categories. So what the model will do is it will simply say, well, this is its sort of own little group. I'll remember that. I can extract some pattern from here and from here, but I can't extract any pattern from here. But I need to get my loss down. So I'll just remember that, individual piece of training data. And that's exactly what we can recover with this sort of attacks. These individual pieces that don't really have anything close. There is not really a pattern to it. So the best the model can do is remember that. It doesn't mean that with this attack, you're going to get this piece of data or this piece of data, right? So if your personal identifiable information is sort of falls into some kind of regular pattern, it's likely to be more safe against an attack like this. That's why they, for example, are able to extract these sort of UUIDs or URLs with random strings in them, because random strings have no pattern, right? So they are likely to be out here away from the other training examples where the best a model can do is actually remember the thing rather than extract a pattern. Now, the other example here with this personally identifiable information, I believe that's just because it appears a lot of times, honestly, not because there's no pattern, but because it appears so many times that the model simply, it's why should it extract a pattern when it appears so often? It can just, remember it like a famous person's name. It seems to be an address that's important if it appears so often, I guess, from the point of view of the model. So that's sort of what this does. Again, it extracts indiscriminately. It doesn't mean that the attack can be leveraged to, get any training data sample back. It's still worrisome, but you have to take into account. Another thing that is really sticking out in this paper is the amount of hedging that this paper does. This almost in every paragraph, but certainly in every subsection, there is like hedging against, why it is okay to publish this research, and so on. So, when they say our attack target is GPT-2, we select GPT-2 is a nearly perfect target. From an ethical standpoint, the model and the data are public. So any memorized data we extract is already public, and so on. And they do this in every piece of text. And, in my video about broader impact statements, that was exactly my point. These large corporations, right? You have many of these authors. I think a fair amount of work went into framing this research such that it sort of can't get attacked from, people concerned about ethical considerations when releasing research like this. Like, this is clearly research that can be leveraged, for bad, if you will. But since these, companies have a lot of resources and they're, can put many people on this, can devote a fair bit of amount of work into framing the problem, that can be mitigated. Whereas if, some lonely PhD student would do the same research right here, the exact same research, I'm very doubtful it would be received as well as this piece right here. And in my opinion, as I already said in that video, this just sort of shifts, a bit more power to these large institutions that sort of can afford the framing right here. They don't have to change anything about their research. But the rest of us do. All right, rant over. Let's continue. So they're going to do this in two different steps right here. And they have a diagram. Yes, they have a diagram. So first, they do this in two steps. Step one, they query the model. They have different queries, right? But they just sort of generate data from the model. So they generate lots of data right here from the model. Then they select from the model a subset that they think these could be memorized training examples. Then they deduplicate it. They select again, and then they check. Okay, it's fairly easy workflow. So step one is generate a bunch of data that you think could be memorized, and then step two, check whether you find these samples in the internet, because all of GPT-2's training data comes from the internet. If you can find them on the internet verbatim, right, that probably means GPT-2 has remembered. Like, the likelihood that it verbatim remembers, a UUID that wasn't in its training data is almost zero. So yeah, this goes by manual internet search. So respect to these authors who have done this. They start out with some fairly weak baseline, which is they simply generate a large quantity of data by unconditionally sampling, and then they predict which output contains memorized text by simply analyzing the likelihood. So whatever text the model finds highly likely, they think that could be memorized, because if you provide a model with training data and you ask it to reduce its loss on the training data, it will assign highest likelihood to the training data. That's that's how these models work. So they assume that if a model has high likelihood or low perplexity, that's the sort of same thing, except, yeah, so you can see here, if the perplexity is low, then the model is not very surprised by the sequence and has assigned, on average, a high probability to each subsequent token in the sequence. And if that happens, they say this could be memorized. This is obviously very, very, very simple. Say This simple baseline extraction attack can find a wide variety of memorized content. For example, GPT-2 memorizes the entire text of the MIT public license as well as the user guidelines of Vaughan Life, an online streaming site. While this is memorization, it is only k-eidetic memorization for a large value of k. These licenses occur thousands of times. Okay. The most interesting examples include the memorization of popular individuals' Twitter handles or email addresses. In fact, all memorized content we identify in this baseline setting is likely to have appeared in the training dataset many times. So here they say it doesn't really work if you just sample and then look at what's most likely, because yes, this will be memorized, but it is sort of a non-problematic form of memorization, like famous people's Twitter handles. This is like famous people's names at this point, right? So now they go about improving it. Okay, so they improve both steps. They improve step 1. Where are we? No, it's down here. They improve step 1 by doing one of two things. Either you want your temperature to decay. So in this sampling, when you sample from the model, you have a temperature that you sample from, and you can decrease that over time. So at the beginning, you can let the model explore a bit, but then you can decrease it, and that's so the goal of changing step 1 is to create a more diverse set of generations, right? So you can sample with high temperature at the beginning and then decrease it over time, okay? Such that you still get sort of high likelihood sequences, but you get different ones. So you start off differently and then you go into the high likelihood regime. The second way they change this is what they do is they go to the internet again. So they go to the World Wide Web, which is, okay, I'm terrible at drawing the globe with. Okay, they go to the World Wide Web and they just get pieces of text from the internet. So they get a website and they just take some tiny substring from here, from this, and they use that as the input to their model. And that's sort of to get more diverse predictions. So if you input a short prefix that you found somewhere on the internet and then let the model continue, that generates you a wide, diverse variety of pieces of text. Okay, so that's how they up the how many different samples the model generates. Because in the initial experiments, they found that the model will sort of output the same things over and over again if you simply query it unconditionally. So either high temperature or conditioned on internet text. The second step is sort of what I find the clever step. So here they have to, before they simply said whatever has high likelihood, that's what we think is memorized. But of course, a lot of these will not be, with low K memorized. A lot of them will simply be high likelihood because they're actually likely. So they say, okay, when are we in this situation? So let's say here is our data set, okay? And here is the MIT public license is here. And it appears like billion times. Like this data point is like ginormous. It's all, the MIT public license. And here is our outlier data point. Now this model will extract patterns, let's say from this, and this is a pattern, and it will assign a single pattern to the MIT public license because it just appears so often, and it will assign a single pattern to this data point down here just because it's such an outlier, right? So how do we devise a scheme that will find this one reliably, but sort of will recognize, wait a minute, this memorization here is okay. But we need to devise a scheme without having access to the training data, right? If a human looks at it, of course, the MIT public license is, seems common. We know that it's common and so on. We know that it's highly likely text because it's a license almost everywhere. If a human looks at this right here and sees, the name and address of a person or a credit card number, we know that's not really highly likely text. And that's sort of the answer right here. So we say if a human looks at it, But what is a human? A human is just another language model, among other things, right? But the human is just sort of another thing that has an intuition of how likely text is. So the basis of their approach is going to be the following. Let's take a second data set, okay? Sampled in the same way, also from the internet, but not in exactly the same way. In fact, they use Common Crawl instead of the Reddit outbound links that GPT-2 used. But we take any other data set, and I'm going to draw the other data set. So here's a data point, here's a data point. Maybe this data point is duplicated from the other data set, and here's a data point, here one. Right, so you're going to have sort of other data points, but also, since you're sampling from the internet broadly, you're going to have the MIT public license many times. And you're also going to have the outliers in this data set. Now, the important part is you're probably, if you sample this differently, in the same fashion, but a bit differently, you're probably not going to have this same outlier right here. You're probably not going to have that in your new data set. Okay, so you can see in the new data set, I hope you can see this, you're going to have the same pattern extracted here, even though it's from slightly different data points. You're going to have maybe a pattern extracted here, maybe one here. You're going to have this same cluster here because the MIT public license will appear, even though it comes from other documents, it's copied over and over, and you're going to have this outlier right here. So what you can do to differentiate our two things, you can consider a second language model, and you can ask. So here you have two things that the first language model thinks are very likely. You have this thing right here, and you have this thing right here. Both the first language model considers super likely. You ask the second language model, and the second language model says, yes, the MIT public license, I consider that to be also super likely. But this outlier over here, I've never seen that. What's that? That seems very unlikely. And so by the ratio of the two likelihoods of the two different models, you can find out samples that the first model finds super likely, but the second model thinks are not likely at all. And that's exactly the trick they use right here. In fact, they use many instances of that trick. So here are the strategies. Perplexity is simply what they used before. Whatever is likely is probably memorized. Yes, it's memorized, but it's often memorized justifiedly. Then they have these strategies, small and medium, and this is the ratio of the log perplexities of the largest GPT-2 model, that's the one they attack, and the small GPT-2 model. And this ties into, so you don't even need a different model, right? You can simply train the reason they train a smaller model is the following. And we, on the Machine Learning Street Talk podcast, if you don't know that, it's a podcast where we talk to people from various, from the industry and from various research labs and so on. And we spoke with Sarah Hooker, who we talked about her paper, The Hardware Lottery, but she also has other research where she sort of shows that if you have weights, so you have a neural network and it has, layers, and you have weights in these layers, right? What she was able to show is that not all weights are equal. So some of the weights, let's say the weights here, will be allocated to this pattern extraction thing. So, here we have these, you have training data, outlier, right? So you'll have these weights representing this pattern within a layer, right? You have this pattern will be represented by these weights right here. And then you'll have other weights that are sort of allocated to remembering single or very few outliers. Okay, so here this will be allocated. And these will be disproportionate. So there will be many, many more data samples covered by, let's say, this piece of weights right here. I should have drawn the bottom one smaller than by this. So there might be 1,000 training examples covered by one piece of weight space, and there might be only one piece of training data covered by this other piece of weight space. And that's simply because it can extract a pattern from one, but not from the other, so it needs to memorize it. And the larger we make these models, the more parameters we give them, the more ability they have, the more space they have to do this remembering. So what Sarah Hooker noticed in her paper is, if you then distill these models, and distillation is the process of taking these models and putting their knowledge into smaller models, then what happens is not all training data points will so that in distillation you usually lose performance. Not all training data points will lose performance equally. Namely, you will lose performance on the training data points that are sort of these outliers, that are these not often represented in the training data, that the model has a harder time extracting patterns from it. So they will be seldom patterns, or just hard patterns. I would also assume that patterns that are harder to extract will also fall away. So the more complicated patterns will also be sacrificed. But I guess among the things are these outliers. So if you train a smaller model, the smaller model would have less ability to remember these outliers, and therefore if you do this, you don't even have to do it on a different training data set, right? You can simply compare to the same model trained on to a smaller version of the same model trained on the same training data set, because that will probably not remember the outliers as much. It would have been interesting if these authors here had actually distilled GPT-2, and though they do not have access to the original training data, so I can get why they didn't do it, but it would be interesting to see that. That gives me an idea, sort of. Maybe there is actually a way to look at the weights, and I get these authors don't have access to the weights, but maybe there's a way to look at the weights and to actually be able to sort of, in some way, spot, right, which of the weights only are associated with single or very few training data points. Maybe during training you can sort of count how many times a weight is updated in a substantial amount, or maybe looking at the attention matrices you can sort of determine what are the kind of patterns that need to happen that lead to this weight being activated, right? So if there's a weight and it's activated by lots of different patterns, maybe that weight is useful for many forward propagated signals. But if there is another weight that's only activated by a specific pattern, right, then maybe that's one of these memorization weights. So maybe there's a way to recognize these in the weights directly. So distillation appears to be sort of a defense against this memorization of things, though that's not done in this particular paper. They also have different strategies, so you don't need to do this neurally, right? You can compare the ratio of the perplexity that GPT-2 gives to the zlib entropy. So this is simply a text compression method. You can even compare it perplexities between the original string and the lowercase version, and so on. So they extract, for each of these configurations, we select 100 examples among the top 1,000 samples. So they produce 1,000 samples, and they sample 100 from those 1,000. So they mostly sample from low-ranked samples, but also they explore some of the high-ranked samples. They have a formula where they sample, they deduplicate, and then they investigate. All right, so they do Google searches. If they can find the thing, they say that's memorized. All right, so they say across all strategies, we identify 604 unique memorized training examples from among the 1,800 candidates. Our best variant has a true positive rate of 67%. That's quite remarkable, right? So 67% of the things that this method delivers you automatically are actually memorized. Though you have to qualify that, right? If you want more than 1,000 examples, that rate's going to drop, right? Since you select the top 1,000 examples, these are the most likely to be memorized. So yeah, if an attacker wants more, if they want to scale this attack up, their positive rate is going to plummet fairly quickly I'm going to assume. It would actually be interesting also to see how that develops with the top retrieved document right here. But I get they have to do Google searches to figure out, and then ask OpenAI to figure out if it's really a memorized training example. They say there are categories. We manually group the memorized samples into different categories. The results are shown in Table 1. Most memorized content is fairly canonical text from news headlines, log files, entry from forums or wikis, or religious text. However, we also identify a significant amount of unique data containing 128 bits UUIDs, correctly resolving URLs containing random strings, and contact information of individual people. Okay, so as I said, this is fairly interesting, but also a bit expected, right? If I give you the start of a UUID, then there is no pattern to extract, except I guess the UUID structure, but there is no deeper pattern to extract. So all the model really can do is memorize the UUID, especially if there aren't too many UUIDs in the training data, or if this particular UUID is some sort of, as I said, it's this outlier type of situations. The same thing for, URLs containing random strings. These are just not pattern extractable, therefore more easily remembered by the model than learned. So you can see right here the breakdown where they say how many of what they extract. And here, contact info, 32, named individuals in non-news, 46. That's a fair amount of things you can extract from GPT-2. Though you have to say that is all, right? All of GPT-2, you get approximately 100 things that are kind of names or contact informations. So as I said, not too bad, specifically considering what I've shown you here, right? That's one of these contact informations. And they do say this in the paper, that this information was obviously released in the context of this software project. And the problem is only the model might actually output this in a different context, right? The model might think, oh, now I need to output some sort of name and address. Ooh, what kind of names and addresses do I know? Well, this name and address appears pretty often. I'm going to put that here. And so that's a failure case, that these things can do. So here is a sort of a graph, and they have more of these graphs later, but you can see that here, for example, is a GPT-2 perplexity, and here is this zlib entropy. And if you plot them one against another, most things will fall on this diagonal right here with the giant blob around here for most text of the internet. And there will be a region where GPT-2 thinks this is fairly low perplexity, but zlib thinks the text is relatively high entropy. So these are candidates for memorization. And the red and blue here are the ones the authors selected for checking, and the ones that are blue are ones that they found are memorized from the internet. So a fairly high percentage, in fact, 67% of this method that they selected was, in fact, was memorized. Though, as I said, you can see that there aren't super many more, right? So this is all samples. I don't know how many, they could generate more, but you can see that it gets pretty sparse out here. Okay. Yeah, so examples of memorized content. Personally identifiable information. They say there are several examples of individual people's names, phone numbers, addresses, and social media accounts. Some of this is memorized content, is just exclusive to a few documents. For example, we extract the usernames of 6 users participating in an IRC conversation that happened in exactly one document. Yeah, so I guess the question is, how often did the usernames appear in that one document, right? And once the model sort of, and how distinct are these usernames from other usernames? Because if they're very distinct and they happen, they have a long conversation, it can be easy to see that the model will remember that. I'm not saying this is not a problem. I'm telling you, the models, it's not that they'll just randomly remember stuff. There needs to be very specific conditions for the models to remember stuff. So they say, we identify 50 examples of memorized URLs that correctly resolve to live web pages. Okay, many of these URLs contain uncommon pieces of text, such as random numbers or base64 encoded strings. Again, this random element right here makes it you can't extract a pattern. They say we identify 31 generated samples that contain snippets of memorized source code. And they can actually extend that. So they can take these snippets and they always, I think they do 256 token length, but they can extend that to sort of verbatim recover the source code. And that's also, that's fairly interesting. And unnatural text, these UUIDs. A Google search for this string identifies just 3 documents containing this UUID. And it is contained in just one GPT-2 training document. Okay, though again, we are not seeing how often. They say table 3 gives 9 examples of k equals 1 memorized content, each of which is a random sequence between 10 and 87 characters long. You can see the table right here. So these are examples of random strings that for some reason appear in this training data in exactly one document. However, this string right here, for example, appears 10 times. And this string right here appears 311 times. So again, it's a random string that appears, though 10 times is fairly often for a piece of text to appear, especially the same piece of text that is not pattern close to any other piece of text. It seems okay that the model remembers that. It seems expected, right? So yeah, here they also say data from 2 sources. We find that samples that contain 2 or more snippets of memorized text that are unrelated to one another. In one example, GPT-2 generates a news article about the real murder of a woman in 2013, but then attributes the murder to one of the victims of a nightclub shooting in Orlando in 2016. And this I found very, very interesting, right? Because that's exactly what I said GPT-3 does, right? Especially, so in GPT-3, they have this example of GPT-3 writing an entire news article about, I'm not even sure, about some pastors, some split in the Mormon church or something like this, or I don't remember correctly, but I was able to Google that. And I did not find the verbatim sequence, but I found that article that GPT-3 wrote many, many times in sort of different words, written down in books and reported about and so on. So what GPT-3 did is simply, I would guess, interpolated between these things. And here they find the same thing. GPT-2 just takes 2 pieces of text and sort of finds that they're close and sort of interpolates between the 2. I would call this memorization 2, and they say, this is memorized text. This is not memorized text in their definition of memorized text, but it is, right? So it sort of mixes up different training data points together. And this, I think, is a strong, it's very strong evidence for how these language models work, in that they sort of take training data points and they just kind of mix them together, and they can do this in a grammatically well-founded fashion. They can also change individual words of a sentence and so on. By the way, it doesn't mean that people are doing anything smarter. Like, there are arguments, like the best arguments I hear are, people are kind of doing the same thing. They're just kind of recount the training samples in a bit of their own words. But yeah, this I found extremely, extremely interesting. And also, what I found from GPT-3 with this Google example was that the problem of memorization may even be way worse than what they analyze in this paper right here, because they look for sort of direct overlap in text, whereas they wouldn't catch strings that are, sort of reformulated. Again, okay. So here lastly they say they can extend text, and this thing here I find very interesting. So they say if they put in this prompt 3.14159, GPT-2 will complete the first 25 digits of pi correctly. Interestingly, when they input pi is this, it gives the first 799 digits. And if they say E is this and pi is this, then it gets the first 824 digits correctly. So they make the point here that the memorization problem could actually be much worse if you only knew what prefix to input. So this strengthens my case for the future job description of a prompt engineer, right? It seems to be that it's quite a sort of magical power to know what to input into these language models to make them output what you want them to output in this context, but also in the context where you actually want to do them, want them to do something useful. All right, and here is where they investigate this number k. So you might have noticed, and this is a bit of the criticism of my paper, up until this point, yes, they have the k equals 1 right here, and they sometimes say that it's only found in very few examples, but essentially they investigate this memorization here pretty much in absence of k, of what they themselves define to be problematic, right? They say, well, it's problematic if it only appears in few training examples, but the analysis here is done quite absent of k very often. And here is where they investigate this. So this is also pretty clever. So the experiments here are fairly clever. They find a one document, a paste bin document. So the paste bin document, where that is sort of a JSON document, and it has lots of links. And I found the document is a giant document, okay? And it's a giant JSON document with these entries. So there's this entries, there is color, and then link, and then here the URL would go on, right? And it is in fact the only document in the internet, at least these authors claim, that contains these URLs. But many of the URLs are repeated many times. In fact, here you can see that these are the continuations of the URLs, right? This one, even though it's contained in one document, it's actually repeated 359 times, and so on. So this is a playground. They say, okay, this document was in the training data of GPT-2. Here we know how often each of these strings appeared in the document. So they can directly make an experiment. How often does a string need to be present for the model to memorize it? They simply order by the number of total occurrences right here, as you can see. And they ask each of these models whether or not it has memorized the string. And they do this by inputting this. So this is the input, and they simply sample. If the model manages to output any of these URLs, they consider that to be memorized. If not, then not. If it doesn't memorize it, they have a second trick that if model can get half a point, if they input this first random sequence, I think they input 6 tokens of this random sequence, and if then the model completes, then they say, it has memorized it, right? So you can see right here, it appears that this large language model needs a string, let's say 20 times or higher for it to memorize it. And you can also see the trend right here that if you go to the smaller models, they need a lot more in order to memorize them because they have less weights. They can't afford to memorize stuff easily, right? They need to extract the pattern. So they'd rather forget about the string, incur a loss, and focus on other training examples. So yeah, two things. In this direction, smaller models. In this direction, larger models. So that means that something like GPT-3 will have this problem much more pronounced. So that's the bad news about this result. The good news about this result is that this is the case where you have fairly random sequences, right? These even, if tokenizing this is not going to be natural text, and there are these, these Reddit URLs have these random prefixes. So this is very much this sort of outlier case. It's a pretty clever case study to find this document, I have to say. But it is sort of good news that this is not the usual case. This is really the case. This data is very, very prone to being memorized, right? Because it's not patternable and it's very random. And yeah, so, okay. So that was that. As I said, the amount of hedging right here is really, really, like, it's a lot. They discuss what you can do with it. You can train with differential privacy, though that doesn't really help, as we said, because some of these strings are included in more than one time. You can curate the training data, which doesn't really help because the training data is too large. You can limit impact of memorization on downstream applications. So if you fine-tune, but we don't know exactly what fine-tuned models forget and what they retain, or you can audit, which is essentially what this paper right here does. And that seems like a good, the best strategy we have so far is to audit these models. And yeah, so I wanted to quickly check out also the appendix. The appendix here shows sort of these graphs for the other methods, and it is very cool if you wanna check that out. And it has sort of categorization of what they find as these memorized pieces of text. But what my main point was right here is that this paper shows a problem, let's say, with these large language models, namely that they memorize certain pieces of training data. While that sounds scary, I feel that the nature of the data that it remembers is very particular. So you cannot extract any piece of training data. The nature is very particular. It's this sort of outlierish training data points. And also, it very, very, very often, it isn't enough that it just is there one time. So even when they say this piece of information is only in one document, very often it appears many times in that document. That together with the sort of non-patternability of the data that it memorizes right here actually makes me fairly optimistic, more optimistic than I would have thought, honestly, about these language models. Yes, so we'll see what the future brings. As I said, this is going to be more pronounced in larger models, and this is not the only problem with these models, as my GPT-3 Google search in that video shows. All right, I hope this was enjoyable. Let me know what you think, and maybe check out the paper. Bye-bye.